Well, I just have the important reminder of making sure that your calculator is in the mode that you think it is, because this will be the second run at the same problem. That's okay, it's good practice. So Susie and Sharon, they're still having bad hair days, and Susie got taller than Sharon, somehow between the last two videos. Now they have a rope that's underneath a wall that has a little gap, and Susie's pulling up on that rope at 36 degrees to the horizontal, and Sharon, and Susie's pulling up at 16 newtons to 60 degrees to the horizontal. We want to know what the resultant force is of these two vectors. But to do that, to add them to get to the resultant like we had done before, we need to break these into the x and y components. And we're going to use a little trig. So bear with me. This is pre-calc, I think, in 5 minutes. We're going to call this angle theta. This is the hypotenuse. This is the adjacent side to this angle. And this is the opposite side to this angle. It's important to emphasize it's to this angle. So this is not always the adjacent. This is not always opposite. It's just when we're looking at this particular angle. We have some trig functions that we can use. So ca toa, sine of theta equals opposite over hypotenuse. Cosine theta equals ca adjacent over hypotenuse. Tan theta equals opposite over adjacent, toa. Opposite over adjacent. Now if I have these two sides and I want to get, or if I have sides and I want to get an angle, that function is called arc. So an arc sine, not inverse, but arc. Oops. Arc sine of opposite over hypotenuse equals that angle theta. Arc cosine, geez, oh Pete. Arc cosine of adjacent over hypotenuse equals theta. And arc tangent, which you'll see we use quite regularly, of opposite over adjacent equals theta. You need to see why we want this, because we're dealing with vectors, so not only do we want to give magnitude and direction, we want the angle, because the angle is a little more specific. It tells us where exactly the final vector is going to live, reference to the horizontal axes. So let's see how we can apply that. Let's start with Sharon. Make sure you can see. Sharon, what is her x component? So let's say 36. If I want the x component, that is the adjacent side. So cosine, I take the hypotenuse, multiply it by the cosine, so 16 newtons times cosine of 36 degrees gives me my x hat component, plus, now I want my y component, which is here, so opposite over hypotenuse, plus 16 newtons times sine of 39 degrees. 39 degrees gives us our y hat component. Now what about Susie? I'm going to do it one way, and I'm going to emphasize how important it is to make sure that you pay attention to the axes if you do it the way I'm going to do it first. So 16 newtons, and we want, say, we'll start with the x component again. So this is the adjacent side to this angle. So cosine of 16 newtons times cosine of, and she's pulling at an angle of 60 degrees in the x-hat. And her y component is right here, and that's that part of the triangle. So opposite, so sine, 16 newtons, sine, my tongue is getting tied, sine of 60 degrees gives me my y-hat component. Right now we're going to button push and make for darn sure that you are in. You can see all the work I did before. Oops, let me make sure you can see this. I don't know that you will be able to. Oh, there we go. So for my calculator, if I click mode, I page down where it says angle, and hopefully you can see I have 3 choices there: radian, degree, and gradient. I want it in degrees before I accidentally had it in radians. Now I know I'm actually doing the math I think I'm doing. I'm going to button push. Hold on. Okay, so I've button pushed, and I get that Sharon is pulling 12.94 in the x-hat plus 9.4 in the y-hat, and Susie's pulling at 8 newtons in the x-hat and almost 19 newtons in the y-hat direction. So now, if we want the resultant, we need to add these two components together, or these two vectors together, excuse me. Now, I'm glad I made that mistake. So the mistake I made was what I emphasized in the beginning, that you can do it this way, but you need to be careful. Then I got talking and I wasn't careful. So let's think about Sharon. So we expect Sharon to be, oops, pull it down so you can see. We expect Sharon's x and y components to both be positive. She's in the positive x-axis and positive y-axis. Susie, however, remember I emphasized that we're taking just this 60. So my answer is going to give me a positive number because my calculator is actually doing a number based on an angle over here, not over here. If I want this to come out correctly on my calculator to where I don't have to go back and put in negative signs, I actually need to measure this angle from here to here. So that would be 180 minus 60, so 120 is what I would need to put in for my angles here. If I did that, then I would get correct positive or negative signs for being on the axes. Because I chose to do 60, it's just visually easier for me to see my triangle and what I'm working with. I need to go back and make sure that I have my x's and y's are correct with a positive or negative sign. So this x component for Susie is in the negative x direction. Susie, let's make sure. Yep. So that is negative, not positive. And she's pulling up in the positive y, so we're good there. So actually I'm kind of glad that I made that mistake. So let's see what it comes out really. Alright, so now we have the components of the y vector. So what does this tell us? Let's see, so here's Sharon, and Sharon turns out to be about 12 on the x, and our resultant is about 4, so we'll make this over here. So we're going to come out about, or 5 rather, and then we're going to go up like 28 newtons, 16, so we'll call this 28-ish. So my resultant vector, starting from the origin, is going to be this way. So the net force is going this direction, and it's defined by these two vectors. But we don't know what the magnitude of that line is. So again, this is just trig. If those lines had been straight, it would be easier to tell that this is a right triangle. So we have our a squared plus b squared to get the magnitude, which will be just c. So our magnitude of our resultant vector is the square root of 4.94 newtons squared plus 28.26 newtons squared. So one thing that I tell my students or suggest to them, if you are not comfortable with your calculator, because the quantity is squared, if this were a negative number, that negative is going to end up being a positive anyhow. Save yourself making mistakes because the calculator is doing something you don't expect it to do, and don't include the negative signs when you do the magnitude. Because like I said, it's going to come out positive. A negative times a negative is positive. So it doesn't matter. It's not going to change your end result. What can change is if you don't know how to properly put in, if you just wrote this in your calculator, you would get a negative answer. In order to get that properly handled, you would have to do that. That's all I'm saying. So just a word to the wise. So what does this come out to? So the magnitude of R is 28.69 newtons, or 28.7 newtons. And so this length here is 28 point, oops, so you can see, 28.7 newtons. But we don't know what the angle is. So I'm going to redraw that. Make sure you can see it. Good. So we don't know what that angle is. Now you need to decide 0.7 newtons, which triangle you want to deal with. You can do either, just so long as you really pay attention to what sides are opposite and adjacent. So if I wanted to find this angle, because I felt like doing an extra step and subtracting from 90 to find out what this angle is, which is the one we actually want, then you just need to really pay attention that your opposite and adjacent sides are going to be different. And I'm saying that because one of the pitfalls that students fall into is they start seeing a pattern where cosine is x, and so they always assume that cosine gives them the x component, and that's not the case. If we change the triangles around, like in this case, I would end up getting a different x and y. I'm sorry, cosine opposite and adjacent side. So let's go with this angle, because that's the one we actually want anyhow. So the adjacent side is indeed the x, and the opposite side in this case is indeed the y. So remember, we have this arc tangent will give us this angle. We have these two sides, so let's go ahead and use it. Arc tangent of TOA, opposite over adjacent, so y over x, and our y is 28.26 newtons over our x, make sure you can see that, 94 newtons. We put that in our calculator. And we get that this angle is 80.1 degrees, more or less. I did some rounding in there. So this 80.1, because we used this angle, is indeed this angle. So from the horizontal is what we always measure everything from. If you don't do that, then you need to emphasize like 28 degrees and turn this in like north, south, east, west, or something like that, so you can denote where this angle actually is that you're measuring. If you give just 80.1 degrees, you're saying from the horizontal. So just be careful about what you're doing. So now, the good news is this process applies to 3, 4, 5, 6, 30, 50, 80 vectors. I won't have you doing 80 vectors because you'd hate me and I'd hate grading it. But it is just that no matter how many vectors we have. So step 1 is getting it into its x and y components, because I can add up any number of vectors here. And after that, then add them up. Well, actually, after that, make sure that you have your positives and negatives as they should be. So always draw a picture. Always, always draw a picture. So double check your positive and negative signs. Add everything up. That defines the resultant vector, so where that net force is going, the direction of. Then we just use Pythagorean, a squared plus b squared equals c squared, and that gives us the magnitude of the resultant vector. So this is the net force. Then we can use our components to get the angle of that net force relative to the axes. And that's it. It's the same process, it just gets a little bit more complicated depending on how you're applying it.